The quantum eraser experiment tantalizes us with the apparent instantaneous flow of information between entangled photon pairs. In fact, the delayed choice quantum eraser seems to show that information can travel backwards in time. For today's challenge question, I'm going to propose a way to use it to create a time-traveling communication device and use it to cheat on the lottery. I want your honest opinion. First though, you really should go back and watch that quantum eraser episode unless your memory is incredible. Good? Let me review the important bits anyway. We start with a standard double-slit apparatus. Photons are fired one at a time through the two slits. On the opposite side, each photon is split into an entangled pair of photons. One of these is sent off to a screen where its location is recorded, while the other is used to identify which slit the original photon passed through. The setup looks like this. In the interest of accuracy, let me add a little detail that I skipped in the previous video. When the researchers conducted this experiment, they didn't bother with detector B. There were really only two sets of possible outcomes. One, a photon finds its way to detector A. In that case, we know the original photon must have passed through slit A. Or two, either detector C or D fire, in which case we have no idea which slit was traversed. And the result is that photons whose entangled twins land at A produce no interference pattern. They just land in a single pile as though they had travelled as particles through the entire experiment. But photons landing at C or D have twins that do produce an interference pattern at the screen. One important extra piece of information: that interference pattern is slightly different depending on whether C or D fire. The pattern for C has peaks that line up with the valleys of the interference pattern from D. But you see the clear patterns when you separate those C and D photons. Okay, so the pattern that forms at the screen depends on whether we gain knowledge of the path of the original photon. But crazily, all of this detecting or erasing of path information happens after each photon lands at the screen, after those photons land according to an interference distribution or a single pile distribution. The information regarding whether the observer knows the path appears to travel back in time, even if it was only a tiny fraction of a second in the experiment that was performed. Okay, so with a couple of slight modifications, I think we can turn this into a communication device that can not only send information instantaneously between 2 points, but can also send information back in time. So my evil genius plan. I'm going to build a version of this experiment that will let me send tomorrow's winning lottery numbers back to myself. Here's how it works. First, let's bring back detector B. We don't really need it, but it makes the explanation simpler. As it was executed, photons can travel to the which way section, so detectors A and B, or to the eraser section, so C and D. That choice is made by these beam splitters, which randomly reflect 50% of photons and let 50% pass through. But what if we could make this choice? Let's replace these beam splitters with mirrors attached to a switch. With the mirrors in place, photons are reflected to the which way detectors, and no interference pattern is formed. But activate the switch and the mirrors move out of the way. Photons travel through to the eraser section, resulting in an interference pattern at the screen. We make the decision of whether to know the path of the original photon or whether to erase that knowledge. This conscious choice should be no different to the random decision of the beam splitter. Now we have a way to send a binary code from the switch, which is located at the which way/eraser end of the experiment, to the screen, which could theoretically be very distant in both space and time. Okay, we need one more alteration. Before the photons get to the which way end, we freeze them for a day. That's long enough to buy lots of lottery tickets before the draw. Actually, you can't really freeze photons, so maybe we bounce them between Earth and the Moon like 8,000 times. Let's just assume we can do that part perfectly. So we turn on our device, photons start hitting the screen, building up some pattern. Once the lottery is drawn, we use our switch to tap out the lottery numbers in binary code. Those numbers will emerge in the interference patterns that were recorded a day ago. Here's my question. Why am I going to be sadly disappointed after I turn on my invention? Oh, I do get a signal. Nice work, future me. And that signal does contain the interference patterns from my future choices with perfect fidelity. But for some reason, I can't read the numbers. What went wrong? Think carefully about this and submit your detailed explanation to pbsspacetime@gmail.com with the subject line Quantum Eraser Challenge Question. Be sure to use exactly these words because we filter by subject line. We'll choose 5 correct answers to receive Spacetime t-shirts. Of course, if you figure out a way to make this invention work, then you should certainly submit your explanation. You'll get a t-shirt and half of any lottery winnings. See you next week for a fresh new episode of Spacetime.